Straight line kinematics. Now again, kind of a review from grade 10. You won't sort of know when I sort of morph into grade 11. It'll just sort of, flow into that kind of thing. And some of you, depending on which teacher you had, might have seen some stuff, and others might not have either. So, all right. So let's talk about straight line kinematics. Any study in physics is best approached by beginning with the simplest form of a concept, followed by adding complexities as each step is understood. The concept of motion and its analysis is fundamental to physics. Consequently, we'll begin our study with this concept. Philosophers and scientists since the beginning of time have observed and speculated on the nature of motion, but interestingly, the concepts they developed for approximately 2,000 years until Galileo's time were completely incorrect. That is unfortunate, isn't it? Right? For 2,000 years, we were led astray. That is unfortunate.
No, you didn't get one either.
Oh. So, our study of motion will begin by analyzing in its simplest form, by analyzing the motion alone without being concerned about its cause, which is kinematics. In other words, we're not going to deal with forces yet. That'll be the next unit. And by allowing the motion to occur in a straight line only. Does anybody remember the crazy word for straight line motion? There's two that I would accept if I was on a game show host. One starts with an R, one starts with a T. What is it? Rectilinear motion. Very good, Lloyd Kale. You win the prize. Rectilinear motion. The other one without rotating is? Translational. Translational. This is called straight line kinematics. In order to study straight line kinematics most effectively, we will look at the simplest concepts first, then use them to develop the more complex ones. It's easy to picture, an easy way to picture straight line kinematics is to use a train as an analogy because its motion is restricted to tracks. And for our purposes, we can assume the tracks are always in a straight line. So, in order to illustrate the concepts of position and displacement, we will use a locomotive moving back and forth in front of a station as it shunts rail cars, moves rail cars back and forth. Remember that the track is straight. The train station is our reference point for analyzing the motion of locomotives. So the train station is marked with a?
1, 0.
Not a 3, a 0. 0. As we stand at the station, we notice that the locomotive is 50 meters to our left. Sometime later, it's right in front of us, and still later, 40 meters to our right, and later still located 10 meters to our left again. We could draw a diagram to represent the various locations of the locomotive as they are measured from our reference point, the station. So what I would like you to do is I would like you to mark on that number line the positions x1, x2, x3, x4, and so on. Okay, now where do those occur? There's nothing to it, right? So, x1 indicates the first position of the locomotive, x2 is so on, right? So where is it starting? 50 meters to our left. So I'm going to put x1 right there, minus 50.
Yeah.
Oh, it's already on there for you guys. Oh. Well, don't I look like the fool?
The first question has to go.
All right, well, x2 is at 0. Turns out this is not so good, eh? x3 is at 40. And x4 is at what? Minus 10. All right. We know that positive to the right, out here is positive, this is negative, blah, 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 blah. If we were to analyze the motion of the locomotive, we would need to know its change of position as it moves back and forth in front of the train station. Anytime there is a change of position of an object, we say that it has undergone displacement. That is to say, flip the page. Displacement is a change in position. Change in position. Now, if we want to determine any change in position, we would subtract where we started from where we ended up. And you probably remember this from the 2D vector stuff, right? And here I've got delta x. Delta x is sometimes written as delta d. They both sort of stand for the same thing. xf minus xi. Final position minus initial position. And the symbol delta, the little triangle thingy, is a much used symbol in physics which indicates a change in something and always subtracts the initial reading from the final. The displacement of the locomotive for the first interval can now be calculated. So my x2 position is 0. I subtract my initial position, which was minus 50. I got 0 minus minus 50, and I get plus 50. And if you go back to here, to the picture, right, you can see that x1 to x2 is a plus 50. 50 to the right. It's pretty simple, really, isn't it? An interesting little aside. What do you think if we traveled over to Athens to a Greek physics class? What do you think they use for delta? Because remember, all of their notes are going to be written in Greek. So what do they use for the Greek letters that we use? Well, when they have delta D, when they write delta D, they would write delta D like this. Because the little triangle is their D. I don't know.
In English,
I don't know, maybe. Or maybe they go like this. Maybe they go like this, or Alex. Maybe they go D delta, yeah. Is that what you meant? I don't know.
That's right.
If you go to Greece, stop some kid on the street and ask him, would you?
31.
you probably would understand.
31.
Yeah. Yeah, that's how they speak.
I did, yes, sir.
Triangle, square, circle. All right, so with your clicker, tell me what's the displacement for x2 to x3? No, you tell me. Correct answer is 40. From 0 to 40. Plus 40 is the displacement. No, you probably don't need a plus. All right, I'll give you another chance. This time, x3 to x4. What's the displacement from x3 to x4? How do we do this time? Yay, 100%. My grade 12 class reminded me of a time last year when I got all excited because I saw 100%, but then I was 100% wrong. And I looked foolish, yeah. They said, do you remember that day, Mr. N? You got all excited because everyone got it wrong. All right. So here's what I want you to do. Now I think, what have you guys got next year, right? All right. So you are to state the displacement for each of the following changes in position. So 1A is question 1, then B, right? C, 4 is D, 5 is E. So just number those. Number 1A, like 1, 2, 3, 4, 5. I'll have to renumber this sheet, looks like someday, right? 6 is 2A, 7 is B, okay? You're going all the way to, when you get to number 3 on your sheet where it says find the displacements, stop so I can put that up.
So you have 9.
Okay, yeah. So do the first 9. Don't do number 10 yet. Do the first 9, don't do number 10 yet, okay? All right, I'm hoping you did pretty well on this, right? The first one, from -8 to -2, that is a displacement of +6. +6, from -8 to -2. In fact, if you were going to do it like mathematically, it would be -2 subtract -8, right? Which is -2 plus 8, which is +6.
Crap.
B is -10, from 2 to -8. That's 10 to the left, -10.
I don't have a
If you were
question.
doing it mathematically, it would be -8 -2, which of course is -10. 0 to 8, oh yeah, everybody got that one right. -8 to 20,
Or did we get it wrong?
no, not yet. -8 to 20 would be 20 subtract -8, or 28. From 8 to -8, -16 is the answer. The symbol delta has other uses. It doesn't have to be displacement. It could be change in anything. Change in temperature from 10 to -20, sort of like our, week in Manitoba. From 10 to 20 is -30 degrees change. If it's the stock market, from 12 to 1750, is that not plus 5.50? I'm guessing some of you just put 5.5, right?
Yeah.
Market wrong.
Yeah. Stupid clickers.
Oh, you have to put 50.
Whatever. Does it matter?
Hurts my mark.
I'm not recording this.
Why not?
You guys are so you guys are all Mark-centric. Person goes on a diet from 60 to, loses 5 pounds, right? So that would be kilograms, thank you. -5. -5.
What's a pound for the
2.2. Oh, now this is one of my favorite questions. A ball falls from a point 20 meters above the ground into a hole 10 meters deep, and you guys did pretty well. That's good. -30, because we go from +20 to -10, right? So it's -10, -20, or -30. Good. And now, which ones displacements have the same? Which one is it? B. Everybody got it right, so that's good. A and C. Awesome. Okay. All right, let's talk more about position time graphs. Now, here's where, if I had to choose a point where it's suddenly no longer grade 10, it's now grade 12, or grade 11, sorry, that would be this point, okay? So it's now time to put the phones away, earbuds out, and really engage in what I'm saying. Because the cruisability here is really low. You know what that means? It means it's not good enough just to be here. Your brain has to actually, be engaged. Position time graphs. Knowing the position of an object tells us something about the motion of the object, but it would be helpful to know the length of time it takes to undergo the displacement. Displacement and time can both be illustrated at the same time on a position time graph, hence the name. The position time graph is capable of providing us with information about displacement, average velocity, and instantaneous velocity. Can anyone tell me the difference between average velocity, I get a little choked up about it, average velocity and instantaneous velocity?
Instantaneous is like at that exact moment.
At that exact moment, and average would be?
Over a period of time.
Over a period of time. That's real good. Good job. These 3 calculations will be performed using the sample position time graph shown below. Okay, so let's talk about displacement. Displacement is determined on a position time graph using the standard formula, delta x equals xf minus xi. But the difference is that the x refers to the, oddly enough, the y-axis. Time is on the x-axis, position is on the y-axis, and for some silly reason we use the letter x to denote position, which means, don't get confused here, right? It's still called the x-axis sideways, it's still called the y-axis this way, but the letter that's on the y-axis just happens to be a x, okay? So, the final and initial positions are located on the vertical coordinate, that's the y-axis, and if you desire, dotted line can be drawn from the graph to the position coordinate in order to easily identify the 2 positions. In the example graph for the time interval A, now you'll see right here, A is this interval right here, from 0 to, 2 seconds, right? So A is from 0 to 2 seconds. What is the displacement? What is the displacement? I went from 0 to 6. I went from 0 to 6. My displacement is 6 minus 0, or 6, right? Now, am I moving up, or am I moving down, or am I moving right, or am I moving left?
Up, right.
I'm moving to the right. Okay, I'm moving to the right. The graph goes up, right? But that's just because the position is on the y-axis. We're talking about rectilinear motion. We're talking about left-right motion, right? So we're talking about a displacement of 6, which is 6 steps to the
left, right.
Right. Just calculating the odds. Right or left, 50%. I'll go with right. You were right. Okay. I'm going to ask you now, do you understand? Determine the displacement for interval B. Here's interval B, here's interval C, here's interval D, here's interval E, and here's interval F. What position do I start at for B? I start at a position of 6. What position do I end up at? Which means my displacement is, don't say it out loud, just put it in. I start at 6, I end at 6. My displacement is?
5.
What's my position at the start of the interval? 6. What's my position at the end of the interval? 6. Have I moved?
Click A is
Have I moved?
to here.
Which means my displacement
0 to
is?
6. You started 0.
How do you
Here.
know that?
It's on up and down. If you start at 6, you're at.
Well,
Yeah.
okay, I see what you're saying. Like that,
Just this.
that's interval A. Yeah, that's A. That's B. You're right. How do I?
It's the up and down.
It's just
Yeah.
like sort of
Like
the
it's like
difference
the
when it
displacement for-
changes shape.
C would be.
Yeah, I see what you're
6,
saying.
10.
That's a good question, Sean. Yeah. Did you get the first one right?
This thing is just like up and down. That's like right.
Okay, so you got to go all the way to interval
11.
F, and then there's number, yeah. So do the first 5. Alrighty. Yay, everybody got number 1 right. 0. How can you tell when the displacement is 0? Line is?
Flat.
Flat. Thank you, Sean. Interval C, I went from 6 all the way down to minus 10. So it's minus 10, minus 6, or minus 16, right? Minus 16. And 90% of you got that right. That's good. Interval D, 0. How can you tell it's 0?
Straight line.
Flat, not straight, flat. Flat. Interval E is up. It goes from minus 10 to minus 4, so that's a displacement of plus 6, right?
You put minus 3.
Plus 6. And the last one is from plus 6, I think, right? No, minus 4 to 0. Yeah. 4. Okay. Given the position time graph below, is this a real-life possible situation?
No.
5% of you said yes, 95% of you said no, so the answer must be no. Can you tell me why this is not possible?
Time can't go backwards.
Well, you can't go back in time. You can't be in 2 places at the same time, Connor. You can't, at 2.5 hours, you can't be there and there, right? How many people remember the vertical line test from math?
I hate
Some of
that
you,
thing.
maybe some of you haven't gotten that far yet. Lloyd, tell us what the vertical line test is.
If you can draw a vertical line anywhere on the graph and it crosses over 2 points, then it's not a linear.
Not a function. It's not a function. You take a vertical line like this, right? And you go from one side to the other, and 1 point, 1 point, 1 point, 1 point, 1 point, 1 point, 1 point. At some, there it's touching 2 places. Therefore, this is not a function. In fact, position is a function of time. You cannot be in 2 places at the same time. Position is always a function of time. There, I just connected math and physics. All right. Now, how much more do we have here? Okay. Oh. This is weird. Okay, that's not what I expected. Okay.